My co-organizer just informed me we're 1 minute late. So let's get started. This is the last session of the day. Uh, we have our last invited talk, but first we have another contributed talk by Gabriel. Take it away.
Thanks. Thanks for the introduction. Also, thanks for this really well thought out workshop. It's really nice. Right, I'm Gabriele. This is joint work with Christian and my advisor, Thomas Sandholm. And before we delve into the content, let me just try to give you a little bit of a glimpse of where this work comes from and what we're trying to do and what you can expect from this talk. In the past few years, a technique called counterfactual regret minimization and its variants have proved to be tremendously successful, in particular in approximating Nash equilibria in extremely large two-player extensive form games. From this, we try to set out and try to isolate CFR's secret sauce that made it so powerful and generalize it to handle an even more generic setting. We just tried to push its generality as much as we could to just try to bank on that kind of performance. And in particular, what we try to do is we take CFR and we generalize it to handle sequential decision making under much more general loss functions and action spaces. And then we show why this is interesting, and by the end of the talk, I'll give you a list and description of some results that we got by using this technique to interesting problems like smoothing games and finding quantum response equilibria, and finally trading off exploitation and exploration in games. Right, so before we start though, let me go through a little bit of the preliminaries and the tools that we will be using for this talk. The first one is extensive form games, and then we will talk about regret minimization. So extensive form games are really ubiquitous models of strategic interactions between players that come up in all sorts of interactions in game theory. And they're very flexible in the sense that unlike normal form games, there are like simultaneous and just like one shot, extensive form games are based on a tree, and therefore they manage to capture much more rich interactions that in particular can involve both sequential and simultaneous moves. So it's a tree-based structure. So of course we have nodes and we have actions and we have observations. For the purpose of this talk, we will only focus on two-player zero-sum games. Two players means that every node either belongs to player one, player two, or nature, which is sort of a stochastic player that plays according to a predefined probability distribution. So what you can see, this is like usually how extensive form games are represented. We have the root of the game. In this case, it's a chance node, and what happens here is that chance will pick an action sampled from a distribution that chooses left with 1/3 of probability and right with 2/3 of probability, and then the game passes to player one, which in turn can pick left and right. Extensive form games are able to capture the idea of having private information. So if you think about a game like poker, you observe the card that you draw from the deck, but your opponent doesn't, for instance, right? So in that case, you have some private information. And the way that we deal with that is that we introduce a new construct on this tree, which is called information set. An information set is, as you can see here, depicted in gray, a set of nodes. And the idea is that those nodes are indistinguishable by the player that has to play there, right? That's because there is some observation that was not observed by the player, right? So the player has uncertainty as to where he or she actually is in the tree. For the purpose of this talk, not only will we assume two players or some, but we will also assume perfect recall, which is sort of a technical condition on these game trees. And this means that the information structure is such that the player can always distinguish based on observations that are done in the past. So in particular, like a player doesn't forget what they've already observed in the past. And this could be either actions performed by the opponent that were public or other type of public observations, like if a card is revealed on the table, for instance, like in the game of poker. So the other tool that we will be often using is regret minimization. And we've already talked about this multiple times in this workshop already, but just as a refresher, the idea of a regret minimizer is that it's this device that is built for supporting repeated decision making, and two operations are supported by this device. First, this device is able to output a recommendation as to what should happen next. So we have like a recommendation sampled from a set X, which is the universe set of recommendations. And the second thing that this device can do is it can receive and observe a loss function, and this loss function is used to evaluate the last decision that was output by the regret minimizer and by this device. And the regret minimization is also called online convex optimization, and it's online in the specific sense that this device outputs recommendations or decisions only based on the past recommendations or decisions and the past observed losses, right? So the new decision is in this sense online. The way we evaluate the quality of this device is via regret. And the idea of regret is to measure how well the device has performed against the best decision in hindsight. So looking at all the loss functions that we've observed, if we could have known them in advance, and if we could have stuck with one decision, what would have been the best decision? This is what the min is doing. And this is compared to what we actually did. That is the evaluation of the loss function in all the decisions that we've output so far. And any good regret minimizer hopefully will let this regret measure grow at a sublinear rate. So this is usually the goal, which is also called Hanon consistency. Right, with that out of the way, what is counterfactual regret minimization? It is a regret minimization framework for extensive form zero-sum games. And as I was mentioning earlier, it's been used primarily to find approximate Nash equilibria. And in the recent years, it's been used with tremendous success, especially in the, with the goal of approximating Nash equilibria in poker games, in extremely large poker games. As you can see, the kind of games we're talking about have an astonishing a number of decision points. In this case, 10 to the 161, which is just huge. There are, in particular, I think you're all familiar with the work like Librates and Deep Stack, which are the two works that did this. And what is the secret sauce of CFR? Well, the secret sauce really is this idea of decomposing the regret that you have on the whole decision tree as a sum of local contributions at each decision point, right? Every time the player has to play in some state, then there exists a notion of localized regret that CFR defines. And in a way, this is like the typical divide and conquer type of approach, where we have the regret on the whole structure, we divide it into individual regrets, and then we let individual localized regret minimizers deal with those localized notions of regrets until the output you can prove has low regret, right? So divide and conquer. From an engineering point of view, this makes a lot of sense, because unlike methods that just try to minimize regret over the whole decision space directly, this allows for pruning, worm starting, and other engineering thing. But CFR also has limitations, and the three main limitations are this. It's for two-player extensive form games only, does not support arbitrary restrictions on the decision space. Say if you want to say from this point on, I don't want to bet anymore in this poker game, and only works with linear loss functions, because that's what it was created for. So what we do is we show how we can lift both of these restrictions, and we provide a more general notion of CFR that uses the same secret sauce, and then we show how to apply it to the other examples that I was mentioning earlier. So the setting that we consider is sequential decision making, and it's a single agent kind of interaction, and it's I think very easy to describe. It's from one agent point of view, and there are three things in this decision making setting. You have decision points where the player actually has to act. There are actions that you can see on the solid lines. And then there are observation points, right? So this, for example, is the decision-making problem that a player faces in Kun poker, which is a simplified notion of poker. And why sequential decision-making is interesting is that it strictly generalizes extensive form games, right? So it's a more general setting. It also generalizes other kind of constructions like partially observable market decision processes and market decision processes where we condition on the entire history of observations and actions. And the other thing that we can do is that we can augment the structure so that those, like X subscript action spaces are general convex sets, not just simplexes like in extensive form games. The kind of losses that we consider on this structure are what we call separable losses. So we are not able to handle all the type of losses, but we handle like a generic class, which is separable losses. And the idea is that we have a loss function for each decision point. And this loss, in particular, the loss functions that we consider are convex. And the loss on the whole structure is just defined as the weighted sum of these losses, weighted by the probability of actually reaching the decision point, which is defined as the product of the probability on the path that goes from the root to the decision point. And as you can see, it's pretty easy to see that this form of separable losses strictly generalizes the linear losses that we have in extensive form games for finding approximate Nash equilibria. So the big question now is, how do we build a regret minimizer for this kind of domain, right? So how do we build a regret minimizer for a sequential decision-making problem? And our solution is laminar regret decomposition. Right? And this is a decomposition theorem, much akin to like the secret sauce that we talked about. Like it takes the regret on the whole structure and it splits it into a sum of regrets for each decision point. And by doing this, like along the way, this also allows us to greatly simplify CFR while we very much extend it. And we simplify it by just really focusing on the important structure of the problem. And again, this works when the loss functions that are localized to each information set are generic. There can be just any convex function, not just linear losses. Right, again, so what is this laminar regret decomposition? Well, the key idea is that we have a localized notion of regret, which is like this R hat. And I mean, the math details are on the poster. They couldn't fit definitely in this slide, but really what we care about is just like this big inequality by the end of the day that just says that the regret on the whole structure is just bounded by this max of the sum, which means that whenever this regret hats go to zero, the whole, grow sublinearly, then the whole thing will grow sublinearly. So we've achieved our goal. And with this, we present 3 applications that we think are very interesting that our framework supports. The first one is regularized opponent exploitation. So imagine this single agent setting where you're observing a static player and you want to learn how to beat him, like how to squeeze as much value from the game as you can. And at the same time, though, you fear that this opponent might start to learn how you're actually acting and just try to exploit the fact that you, in turn, were trying to squeeze as much value as you could from him. So what we do instead is, instead of simply finding a best response to his strategy or her strategy, what we do is we find that best response plus a regularization term that tells us how much we are going away from safety, like how much we are getting ourselves exposed by not picking a safe Nash equilibrium strategy, right? So in particular, what we do is we solve a game where we regularize our objective function with this form of distance from a Nash equilibrium. This is sort of like, you can think of it like as a metric. And what we see is that by doing this, we're able to trade off the exploitability and the utility that we get from the player for different choices of how much we want to regularize our problem, right? In particular, if we care less and less about being safe, of course, we can squeeze more value out of the player, and of course, at the same time, though, we're opening ourselves for exploitability much more. The second setting that we consider is that of finding a quantum response equilibrium, and there's some recent work by Coulter and Ling that shows that in fact, finding a quantum response equilibrium can be done if you regularize your game with like an entropy function. So basically, what we do is at each decision point, we just inject an entropy, like the entropy function, to regularize our game, and then we compute like a subtle point of the problem that includes those regularizers. And the previous approach for this problem, we're using a second order method, which is known not to scale for very large game. Instead, we use our framework, and we show that not only we can scale, but we're, by the fact that the problem is now strongly convex, we actually converge to the saddle point much faster than CFR and its variants. Okay. And the third example that we show to show the power of our framework is that of using strong convexity, basically like smoothing the game, making it strongly convex, so that we can converge to a saddle point faster. And the kind of strong convexity term that we introduce is like the standard quadratic pole. So what we do is for each decision point, we just inject a quadratic regularization, and then we want to find a saddle point of this problem. And of course, strong convexity makes the convergence of our algorithm faster, as you could expect. And what's interesting is that it actually makes our convergence orders of magnitude faster, right? So here you can see the benchmark, the best variant of CFR, which is called CFR plus. And then for different amounts of regularization, you can see the residual, the saddle point that we achieve as the number of iterations increase. And you can see that we can be 2 or 3 orders of magnitude faster than the best state of the art for the non-regularized problem. And for the future, like we're particularly interested in trying to understand, for instance, if this idea of using strong convexity, smoothing out the game, can be powerful enough to let us converge to saddle point, even like Nash equilibria, faster than the state of the art. So to conclude, we extended the CFR paradigm to sequential decision making, which is like a new framework, where we allow general convex functions, so particular regularizers, strongly convex regularizers, and we also allow arbitrary constraints on the action sets, and then we show how to use this technology in a variety of novel settings that we think are promising for a variety of like applications in the real world. Thanks.
Thank you. So any questions for Gabriele? I have a quick question. Can you elaborate a little bit on how you compute that entropy term that you add as a regularizer?
Okay, so what we do is we take the entropy term and we add it to each decision point, and then remember that we have that notion of regret hat that is localized to each decision point. So what we do is we use a regret minimizer like at each decision point to handle like the sum of the linear term plus the regularizer, and we just use like an out of the shelf regret minimizer for that, right? So our
at each point.
Right. Again, so what we do is we have a notion of regret that is localized to each decision point, and then we have the decomposition theorem that says that if every localized regret goes to 0, then or like grows sublinearly, then the overall regret also grows sublinearly. So that's how we do it.
All right. Thank you.
Thanks.
Any more questions?
So these last 3 applications, can you also solve them centrally, with a centralized algorithm?
Yes, you can.
Because these are not interactive settings; these are static settings.
Well, I mean, the online exploitation of the opponent. This is more of an online kind of setting. So we were introducing some noise in the learning. To simulate, like a noise around like a unknown strategy of the opponent.
So, but if I know my opponent, I can also offline decide how to exploit him optimally and then implement.
Absolutely, yeah. You could use tools like online mirror descent or like all that machinery. But we think that the idea of splitting the regret into localized regret at each decision point and then conquering each of them individually is engineeringly very interesting, because then you can do things like deciding that parts of the tree you care less, so like you just prune those, or you can warm store different parts of the tree at different times. Yeah, I think divide and conquer was definitely one of the reasons for the success of these techniques like CFR, CFR Plus in actually real world games.
Yeah, so I guess about the real world games, if I have the time. So you can apply this framework also for cases where you cannot actually contain the whole tree in your memory, right? Like in cases where you have to compress the states.
Right. And there is some interesting work on that for CFR in particular. There's like some work by Noam Brown, for instance, that shows how you can basically freeze parts of the tree and get back to them later, and things like that. So yeah, definitely.
All right, let's thank the speaker. All right, and for our last invited talk, need some help?
Should be fine.
We have Polina Granarova. Does it sound right? Okay. She's a PhD candidate at ETH in Zurich. And again, need some help? All right. And she's going to give us a different interpretation of GANs via online learning and game theory. All right, thank you.
Hello, everyone. Today I will focus on GANs and argue that looking at them through a game theoretic and online learning perspective gives us a new way of handling the common challenges when training GANs. So I was happy to collaborate on this work with colleagues from ETH Zurich, Kafir, Aurelian, Thomas, and Andreas. So what makes GANs particularly interesting is their objective function, where we have two players, namely the generator and the discriminator, acting as the min player and the max player, thus respectively trying to minimize and maximize the same value function. The solution of this objective is the Nash equilibrium, where in theory the generator distribution matches the true data generating distribution. And this is exactly the goal we have in mind when we are training GANs. So this makes GANs inherently a saddle point optimization problem. Saddle point optimization problems are fundamentally different to the typical minimization tasks that the machine learning community is used to, and this gives rise to new challenges. So in particular, two of the most prominent challenges in GANs are in terms of optimization. So how do we find the solution of the game or the Nash equilibrium? And in terms of evaluation, for a given proposed solution, how can we evaluate the quality of the solution, and can we actually measure how far it is from the actual solution of the game? So these two in particular are among the research frontiers of GANs. So here we have a comparison between the likelihood-based case and a saddle point problem. On the left-hand side, we have a simple likelihood problem with a solution at 0. And on the right-hand side, we have a saddle point problem. So here, x and y are scalars, and the first player is controlling x and is trying to minimize the value, and the second player is controlling y and is trying to maximize the value. And here the value is just the product of the two, which makes this game a simple convex-concave game, and it actually has a solution. The Nash equilibrium, it is at 0, 0. So now let's see what happens when we use a gradient-based algorithm to try to find the solution in the two cases. So in the likelihood-based case, we typically don't have a problem. Even when we are training deep models, we are using some optimizer to minimize the cost function. And there are things that can go wrong, such as converging to a local minimum instead of a global minimum, or being stuck at a saddle point, but for the most part, we don't really worry whether the algorithm is going to converge. However, on the other hand, when trying to find an equilibrium to a game, it is actually pretty difficult to guarantee convergence to an equilibrium, or even that the training is going to stop at some particular point that isn't the equilibrium that we are after. So this example here in particular was shown by Ian Goodfellow at NIPS 2016 to demonstrate that when training using SGD, even on simple convex-concave games, we may face the problem of non-convergence, and this is even more apparent when training games like GANs that are known to be non-convex, non-concave. So here, if we update the parameters of both players using gradient descent simultaneously, we analyze gradient descent as a continuous time process, and we look at its trajectory that it's going to take based on its dynamics, we find that a solution has a sinusoidal basis, which makes the result a circular orbit. So the only thing that differs in the circular orbit is based on the initial parameters, and that determines the radius. What it basically tells us is that unless we're lucky enough to initialize it exactly at the origin, gradient descent will never approach the solution of this game, which is the origin. So this gradient descent will then be circling forever around the orbit, and it would never converge. And this non-convergence problem, and in general finding a solution to a game, is one of the central problems of GANs. Another problem for settled points that is inherently different to the likelihood case is in terms of evaluation. And this comes mostly in two flavors, so comparison of different models and having a metric that can be used for monitoring throughout the training. So in particular, if a practitioner is trying to decide whether the model has converged, looking at the train and validation curve in the likelihood case is very useful, whereas looking at the discriminator and generator loss for training again, it is known to not be meaningful. So here we can see that the generator and discriminator loss tend to oscillate a lot, and this makes sense because GANs are zero-sum games, so the gain of one player results in the loss of another player. And having this oscillating pattern is very hard to parse for a practitioner and to decide whether the model has converged or not. This is directly related to having a stopping criteria, so deciding when to stop the training and determining whether the model is still improving or not. So while this can be done by looking at train validation curve, the same is unclear by looking at the discriminator and generator loss. So it is not uncommon for practitioners to do visual inspections of samples to determine when to stop training, or to use some domain-specific metric as a proxy. Also, we face a similar problem when we are trying to tune some hyperparameters. So if we can imagine having several validation curves for the likelihood case, this gives us a good handle for which hyperparameters are better, whereas if we have another set of discriminator and generator loss, this makes it very non-intuitive, and it's very hard to determine which model outperforms the other one. All of this boils down to having a meaningful curve for GANs that practitioners can use throughout training to monitor the training of the models. So these 2 points would exactly be the focus of this talk. So first, I will frame GANs as two-player zero-sum games, which lets us leverage both from game theory and online learning to approach these questions. So in the first part of the talk, I will focus on the optimization part, and I will present an algorithm that is inspired by online learning, which has provable convergence properties for semi-shallow architectures. And semi-shallow architectures are GANs in which the generator is general, so it's a deep network, and the discriminator is concave, so it's just a single-layer neural network. Based on this, we develop efficient heuristic for training deep models, which exhibits better performance and convergence properties in practice. In the second part of the talk, I will focus on the evaluation problem for GANs and argue that the duality gap is a natural metric for measuring the distance to the Nash equilibrium and can be used for monitoring the progress of the training of GANs. Both of these papers can be found on arXiv. So before we dive deeper into optimization and evaluation, I will first formally establish GANs as a zero-sum game, so through a game theoretic framework, and establish what the goal of the game is. So GANs are a zero-sum two-player game. And a zero-sum game is defined by two players, here the generator and the discriminator. The value function of the game, M, sets the utilities of the players. And concretely, upon choosing a strategy UV from the two players, the utility of the generator is minus M of UV, and the utility of the discriminator is M of UV. And the goal of each player is to maximize their worst-case utility. So this formulation makes sense if there exists a pair of pure strategies, U star, V star, such that if approached, neither player can improve its utility by unilateral deviation. So if we have such a point, we may converge to such a point, and this point is known to be a pure equilibrium. However, the problem with having this as the goal when training GANs is that we know that a pure Nash equilibrium may not always exist. So pure Nash equilibrium doesn't exist even for simple games such as rock, paper, scissors, and we actually don't know whether it exists in the common GAN formulations. So for our algorithm that optimizes GANs, the first thing we propose is to change the goal of the game. So instead of aiming for finding the pure equilibrium, we decide to go for the mixed Nash equilibrium. A mixed Nash equilibrium is defined by a pair of distributions such that both players, instead of choosing a single action, choose a distribution over actions. And when we are at a mixed Nash equilibrium, neither player has an incentive to change their distribution. So this raises the question as to why this is the better goal than finding the pure equilibrium. So first, it always exists, and it was also proven by Aurora that it exists for GANs as well. What is even more interesting is that the min-max value for a pure strategy equilibrium is always higher or equal than the min-max value for a mixed strategy equilibrium. So what this means is that if we find the two equilibriums in game, the pure and the mixed equilibrium, the min player, which is the generator and which is what we usually care about when training GANs, will achieve a better worst-case utility. And this means that if we find the most powerful discriminator to play against, the generator playing with mixed strategy will always do better or equally well as a generator playing with a pure strategy. So apart from having a mixed Nash equilibrium that always exists, which is a meaningful goal because if we're after an equilibrium that doesn't exist, we may not converge, and it having a better min-max value, there is also a large body of literature in online learning that we can leverage for how to find a mixed Nash equilibrium in games. So before I move to our algorithm for training GANs and its provable convergence properties, I will first briefly go over the online learning framework and how it is used for solving min-max games. So online learning is a game that lasts for T rounds between a learner and an adversary. So at every time step, the learner selects an action, UT, out of a decision set K, and the adversary responds with the loss function f of t, upon which the learner suffers ft of ut. So here, typically, the loss functions are selected from loss functions that are linear or convex, and the decision set K is also typically assumed to be convex. The performance of the learner is measured by the notion of regret, which is the difference of the cumulative loss compared to the cumulative loss if the best strategy was played in hindsight. And what we are interested here in online learning is for finding algorithms that are known to be no regret. So when using an algorithm that is known to be no regret, we achieve sublinear regret with respect to any sequence of losses. So that means that as time goes by, the learner would do as well as if it had played the best strategy in hindsight. Well, there exist several algorithms for no regret in the convex case. Most of them stem from follow the regularized leader, or FTRL. FTRL has a very simple rule that selects strategy for a learner, and what it does is the following. So at every time step, it selects the strategy that minimizes the cumulative loss over all the previous losses that have been seen so far, plus some regularization term. And the regularization term is here so that it is ensured that the learner doesn't change the decision very abruptly in consecutive rounds, and this is often the crucial part in order to ensure no regret. So FTRL is not known to be no regret in general, but it is a no regret algorithm in the convex case. Now let's see how we can use FTRL as a no regret algorithm or another no regret algorithm for solving min-max games. So here we have a zero-sum game with two players, G and D. At every step, both G and D generate a sequence of actions, here denoted by U and V. And if both players select these actions U and V by using a no-regret algorithm, then the history of the game is guaranteed to converge to the mixed Nash equilibrium. So here, if we put this into the framework of online learning, both of these players, G and D, are the learners, and the loss that they see from the adversary basically depends on M, which is the value function of the game, and the action of the other player. So this is a seminal work in in game theory and online learning that says that as long as we have algorithms that that ensure no regret for choosing the strategies of both players, they end up doing as well as if they had played the best strategy in hindsight, and this guarantees convergence to the mixed Nash equilibrium. So what happens if we use now FTRL for the training of GANs? So if we update both players using FTRL, for the convex-concave GAN, which is, for example, the example that we saw previously, x times y, we have direct convergence to the equilibrium. What we extend our work to is provable convergence in semi-shallow architectures. As I said, semi-shallow architectures are architectures when one player is general, so here we assume the generator is a deep network, and the discriminator is only a one-layer network, so it's concave. So how do we go about proving convergence and solving semi-concave games? So again, the important thing to prove is that when using FTRL to update both the generator and the discriminator, it ensures no regret for both of these players. So for the discriminator side, this is pretty easy because FTRL is known to be no regret algorithm in the concave case, and the discriminator has the assumption that it's concave. For the generator, this is in turn not trivial because we assume no special structure on the generator and its function. So this is not trivial to show, but what we can show is that actually the loss functions that the generator sees has a special structure such that they are stable, and this is due to the decisions the discriminator makes, which are very similar to each other in following steps. And this in turn allows us to prove no regret for FTRL for the generator side as well. And what this means is that with rate of 1 over square root of t, we converge to the mixed Nash equilibrium. So we name our algorithm Chekhov GAN, and this is based on the dramatic principle of Chekhov that says that every element that is introduced in a story should later be used in the story. And in a similar way, every loss function that we introduce in GANs is later used for the optimization in GANs for our algorithm. So let's see how this works as an algorithm for GANs. So when we try to update the generator, we update it using the FTRL rule. So here, the FTRL rule is applied to all the previously seen losses by the generator that are here denoted by F, and they depend on the value function of the game M and the decisions of the discriminator. And the rule is to minimize this cumulative loss and some regularization term. So this translated with words means that we update the generator such that it fools not only the most current discriminator, but it fools all of the previous discriminators. So it saves snapshots from the discriminator, and we try to fool all of them at once. Similarly, we use the FTRL rule to update the discriminator, and what this means is that instead of using the most current generator, we update it such that it classifies correctly from all of the previously seen generators. And then finally, we output uniform distribution over the history of generators and discriminators, and this is guaranteed to achieve approximate mixed Nash equilibrium with a rate of 1 over square root of t, and as the time progresses, this approximation gets closer to the true mixed Nash equilibrium. So in practice, obviously, it's very hard to keep snapshots of all the previously seen models for the generator and discriminators. So what we do is we summarize the history in some way such that we keep only k representative models of generators and discriminators. And instead of taking the full FTRL optimization, we just take a gradient step with respect to the FTRL losses for the generator and discriminator. Now let's see how this performs in practice. So a typical example in GANs is this mixture of 8 Gaussians centered around a circle. And for a special set of hyperparameters, you can make the GAN exhibit non-stable convergence. So it basically generates one particular mode, then it moves to the next one, and then they keep chasing each other with the discriminator in a circle, and the game never converges. So K on the side denotes how many past models we keep. So when K equals to 0, this is the normal GAN case. And we can see that we increase K to even just a few models. So here 5 and 10. We converge to the true data distribution, and we cover all of the modes. So this is very intuitive to see, because when the generator is playing against a discriminator, if it's playing against one, it is just trying to move to another mode. But if it's playing against previously seen discriminators, which know all of the previous modes, then the tactic of the generator is to spread its mass and to not do mode collapse. So in the paper, we have many other experiments on real data, and we show improvement in FID for GAN-based and WGAN-based models. But in interest of time, I'm not going to go through the experiments, but you can find them in the paper if you're interested. So to conclude this part, I've shown an algorithm that has provable convergence for semi-shallow architectures to a mixed Nash equilibrium. And on the practical side, the algorithm exhibits improved stability and performance. So there are still open questions, and these go mostly in terms of how can we bridge the gap between theory and practice more. So on the practical side, the question is whether we have some better ways to summarize the history. So for example, using distillation. Instead of using snapshots of past models, whether we can have only one model and distill the entire knowledge of the history in this particular model. On the theoretical side, the question is whether we can extend the theory to a more general case, and whether there are some other online learning techniques that can be used for solving the GAN game. Now I'll move to more recent work that focuses on evaluation of GANs that is supposed to answer all of the previous questions for monitoring. So what we propose is to use the duality gap, which is well known in optimization, for the evaluation of GANs. So how does the duality gap work? It evaluates a pure strategy, U star, V star, and it's defined by the term that maximizes over V's when U is fixed, and from this subtract the minimization over U's when V is fixed. So what is interesting here is that when we are at the solution or the equilibrium, min-max and max-min are equal, and they have some equilibrium value. And what the duality gap does is, very interestingly, it measures the distance to this equilibrium without knowing the value of the equilibrium A star or what this equilibrium exactly is, which is very convenient for GANs because we don't know the value of the equilibrium. In a similar fashion, we can define a duality gap with mixed strategies. So the properties of the duality gap that are quite nice when used as a metric are, first, that it's always non-negative, and the duality gap is 0 only if we evaluate a pair of actions that is exactly the pure Nash equilibrium. What this means from a game theoretic perspective is that it measures the discrepancy of the max player being the second to commit to a strategy versus being the first to commit to a strategy. So usually when we are playing two-player games, it is always better to be the second one to respond with an action because we already know the action that the opponent has played. However, when we are at the solution of the game, the mixed or the pure Nash equilibrium, it doesn't matter what the order of the players is. And then in this case, the max and the min term of the duality gap are equal, and the duality gap is equal to 0. So here we have an example showcasing how the duality gap measures the distance to the solution. This is a simple quadratic function with a saddle at 0, 0. Now let's see if we try to evaluate a solution that is proposed 0, 0, what we get as the value of the duality gap. So first we compute the max term of the duality gap, which is this line here, and we try to find the maximum over this curve, which is given with this red dot. If we compute the second part, or the mean part of the duality gap, that is this curve here, and the minimum is again given with the red dot, so they coincide, and if we compute its value, the duality gap is equal to 0. Now if we try to evaluate a point that is further away from the equilibrium, so -4, -4, we compute again the max term and the min term, and we can find that the value of the duality gap is equal to 32. As we move further away, the duality gap becomes 61. So here we measure for every point how distant it is from the equilibrium without actually specifying that the equilibrium is the point 0, 0. So this is very convenient for GANs, as it gives us a handle for how far we are from the solution and whether we have converged or not. So how the duality gap is defined for GANs is the following. So if we want to evaluate a pair of generator and discriminator that we have obtained by using training of GANs, so here G star and D star, we compute it such that we fix the generator, G star, and we try to find the most powerful discriminator against this generator, so the most adversarial discriminator that would give this generator the highest loss. Then we also do that for the discriminator, so we fix the discriminator, and we try to find the most adversarial generator that would fool this discriminator the most. So the properties are, again, that it's always non-negative, and it is 0 only if we are exactly the solution, so G star and D star are at the Nash equilibrium. And finally, we also show that the duality gap is always larger than the Jensen-Shannon divergence between the real data distribution and the fake distribution that is obtained by the generator. So this is very convenient because Jensen-Shannon divergence is hard to compute, but as I show next, the duality gap can easily be approximated in practice. So this exactly leads me to the question how to compute the duality gap in practice. So the first step is to train again and obtain a pair of generator and discriminator that we want to evaluate. And for this, we use a training set. For the second step, we find the most powerful generator and discriminator against this fixed G and D, which we call G worst and D worst. And for this, we use a second training set called adversary finding set. And finally, we plug this most adversarial generator and discriminator and the fixed generator and discriminator to the value function of GANs and compute the duality gap. And in order to obtain an unbiased estimate, for this we use a third set, which is called a test set. So in terms of computational efficiency, the first and the third step are not a problem because the first one is the usual GAN training, and the third step is just computing a value. The problem is the second part, which assumes finding an argmin and argmax. So how we approach this in practice is we optimize using a standard gradient-based algorithm, and we use a fixed number of update steps to train G worst and D worst. And in order to speed up the optimization, we initialize the two networks G worst and D worst using the parameters of the GAN. So now let's see how the duality gap can be used by a practitioner. So here we have the typical toy problems in GANs. We have the duality gap progress for stable on the left side and non-stable GANs on the right side. And below, we have heat maps of the generated samples. So here we can see that in this particular case, at this point, the generator converged and it covers the true data distribution. And we can see that this is exactly reflected by the duality gap, which becomes 0 and then shows a clear trend of convergence. So if you're a practitioner trying to decide when to stop the training, this example is 2D, so it's obvious to see, but imagine this in higher dimensional problems. If you look at the generator and discriminator curves, they oscillate and you cannot see this point, but with the duality gap, this is clearly reflected for all of these models. On the right-hand side, we have unstable GANs, and we tweaked the learning rates in order to make the GAN exhibit non-convergent behavior and just keep generating different modes and never converging to a particular point. So this is also reflected by the duality gap trend. As we can see that it goes up, it oscillates, and the value of the duality gap is actually pretty high. So in this case, it's 14. What you can also do with the duality gap is detect stable mode collapse. So here we have a GAN that is trained on MNIST, and we find that after some number of steps, the generator just generates from one mode or a class, and here it is the digit 1. So this is reflected in the duality gap trend such that we see a trend of convergence, but the value of the duality gap is higher than 0. Finally, we wanted to show that you can use the duality gap on any data set, not just the image domain as some of the metrics do, and that you can easily apply it without any modification to any GAN function as long as it's minimax based. So here, this is a problem for physicists that is supposed to change n-body simulators, which are very expensive for the simulation of mass density slices of the universe. So the idea is to train again to replace them. And here on the left side, we have real samples showing slices of the universe. And on the right-hand side, we have fake samples from our trained WGAN model. So now the good part here is that we actually have ground truth metrics for how we evaluate the quality of the generated samples based on some statistics that are actually very different than the statistics of natural images. So in particular, physicists use 3 scores: mass histogram, peak histogram, and power spectral density, and they take the squared norm distance between these 3 metrics for the real samples and the fake samples. And here on the left-hand side, we have the trend of these 3 scores and our duality gap metric, and we are interested to see whether they have correlation. And also these 3 metrics are very expensive to compute in practice, but the duality gap is very efficient. And we do find, in fact, that there is high correlation, and whenever there is a peak for one of the metrics, our duality gap also has a peak. On the right-hand side, we just show Pearson correlation between the duality gap and all these scores in raw form and normalized form. As a byproduct of the duality gap comes the first term that we call the minimax term. It's basically for a fixed generator trying to find the most adversarial discriminator. And this is useful if you just want to evaluate the generator, since the duality gap evaluates the entire GAN at once. So if you have a batch of samples that you want to evaluate, you can just use this term. And the computation that we follow in practice is the same as the one I showed for the computation of the duality gap. So here we are interested in how this loss, the minimax loss, captures mode sensitivity. So in particular here, we compare it against minimax. So minimax is ours, and that is lower is better. Then we have FID, which is a distance, so again, lower is better, and inception score, where higher is better. So here, under A, we have dropped modes. So at the beginning, we have the most dropped modes, and as time goes, we add more modes, and we are interested in the trend of the 3 metrics. So we can see that this is reflected by both the 3 metrics, so they all detect mode collapse. In the middle, we have invented modes. So we put some modes to the generated samples that are not present in the real samples. And we can see that this is captured by minimax and FID, but it's not captured by the inception score. And finally, with C, we have intramode collapse, which measures how much variation you have between the generated samples within one particular class. So minimax and FID capture this quite nicely, whereas inception score is not so sensitive here. And here the good part about the minimax score is that it requires no labeled data or a pre-trained classifier, whereas FID and inception basically depend on this. We also wanted to check how minimax is able to capture visual sample quality. So here we have images from CFAR 10, on which we apply some disturbance, which is basically adding Gaussian noise, adding Gaussian swirl or blur with a Gaussian kernel at increased intensity. And we are again interested in the trend of the metrics. And we see that the minimax metric captures this quite nicely and really reacts to sample quality. So one thing about metrics is that we really need them to be efficiently computable in practice, because ideally we want to be able to compute a metric throughout the training. And we checked bulk log time for inception, FID, and our metric, and we find that they all exhibit this. And in fact, minimax is faster to compute, as well as our duality gap, since we fixed the number of update steps. So one question that rises is what happens if when we are trying to find the worst generator, we have mode collapse? Because we know that mode collapse is a problem of GANs, is this a problem when we're trying to compute the duality gap metric? So in particular, assume we have the same problem as before, so a mixture of 8 Gaussians in a circle, and we have trained again that hits the pure equilibrium. So here we have a generator that covers all 8 modes, and a discriminator that gives 0.5 for all the modes for fake or real, as it cannot distinguish what is real and fake. So now when we are trying to compute the duality gap, we have to compute the worst generator and the worst discriminator. So here with green is the worst generator, and we assume that here we have mode collapse, and the worst generator just covers one mode. So as we know that the GAN that we are evaluating is at the Nash equilibrium, the question is whether the duality gap is still 0. So theory-wise, if we plug this into the formula of GANs, we see that, in fact, the duality gap is 0, and mode collapse for the computation of G worst is not a problem, as long as it is able to cover something where the discriminator thinks it's real. So we did the same thing in practice. So here we have a GAN that we trained, and these are heat maps from generated samples from the GAN, and below from real samples. And you can really see that it covers nicely all of the modes. When training the worst generator for the computation of the duality gap, we indeed find that there is collapse. So basically, it really just tries to find one point for which the discriminator thinks it's real, but we also see that the duality gap is very close to 0. So note here that the duality gap is close to 0 for the GAN that we are evaluating, which is a perfect GAN for this example, and this one that is collapsed is the one that is used for the duality gap computation. So if the GAN that is being evaluated was mode collapsed, then we would have detected this as shown in the previous examples. So to sum up this part, if you're a practitioner, if you want to train GANs, the duality gap and minimax metric have very nice properties. So the duality gap can be used as a monitoring tool for GANs, and it can answer the question of whether the model has converged, when to stop the training, and it gives you a meaningful curve for debugging and tuning. In turn, if you're just interested in the performance of the generator, you can use the minimax metric, and it detects mode changes, and it's also very sensitive to sample quality. And the good part is that it requires no labeled data. It's domain independent, so if you're training again on some specific domain, you can easily use it without any modification. And it can be applied to any GAN formulation as long as it's minimax-based. In terms of research, there are several opportunities to explore. So it is interesting to see how the duality gap can be used for comparison as value to value for GAN, for different GANs with different objectives, such as WGAN and GAN. It is also an interesting question to know whether we can actually optimize the GANs by minimization of the duality gap. And finally, the duality gap can be used in terms of research for pushing research efforts. So in particular, the problem of having not having a metric that can reliably detect non-convergence for higher dimensional problems has been pointed out at ICML 2018. And this metric can actually be used to actually analyze which GAN models converge and which don't. And the last part is that a common research interest right now in GANs is to understand the effect of regularizers on top of the same objective function. And one can actually analyze how these regularizers affect the curve, which is meaningful, and whether they smooth the training. So with that, I thank you for listening.
Thank you. Wonderful talk. Any questions for Paulina? Okay, I'll take the question in the back first.
So I have a question about the first and the second part of the talk. Would it be fair to say that in both the calculation of the FTRL step and the duality gap, you are essentially replacing an argmin operator by a gradient step?
Yes, that's correct.
All right, so isn't there a huge leap of faith involved in saying that you can calculate the minimum of a non-convex multimodal whatever function by one or just few gradient steps?
Yes, there is. So basically for the first problem, we convert the problem of training GANs to this offline optimization, so finding the best response And in practice, we do find that actually just a single gradient step performs quite nicely and outperforms the standard training. And in terms of the computation of the duality gap, we find that as long as you keep the same number of update steps for all the models that you're comparing, it's a lower bound to the distance, so it makes sense.
But so then again, in the FTRL case, if in practice what you're using is just a gradient step, in what sense is the proposed algorithm, the implementation rather, any different than just stochastic gradient descent?
So basically, the generator is non-convex, and we are using the gradient of FTRL, which is the cumulative loss of all the losses that the generator has seen previously. So that's how we use it in practice. So we basically keep snapshots of all the some discriminators, and we try to fool all of them, not just once. And this is a non-convex case.
Okay, thanks. I'll ask you more offline. Thanks.
Okay, maybe one more question. If there's a question. Okay, Simon has a question.
Yeah, so just to be clear, because like as you said, to compute the duality gap, you're solving non-convex. In general, you could get negative duality gap, but you initialize at U star V star, and that's why you always get positive duality gap. Is that correct?
Right. In theory, the duality gap is always positive. In practice, it can happen that you get a negative value. But the interpretation of how we compute the duality gap in practice makes sense intuitively as how much you can attack the generator, so how much you can exploit the generator and how much you can exploit the discriminator. And this gives you a value. So if you use the same number of steps for the evaluation of all your algorithms, they should be directly comparable.
But did you get negative values in practice?
No, in practice, no, we didn't.
All right, let's thank, okay, one more question, fine. Fine. You seem eager.
Oh, just a comment to follow up on that. We also experimented a bit with these notions of exploitability. And then essentially if you fail to appropriately initialize your neural network and compute a best response and you find a very poor solution, you can end up with these negative points. But yeah, essentially you can try again.
More of a statement. Thank you. Let's thank the speaker again.
Thank you.
Okay, another spotlight session. So I would like to invite our spotlight presenters to start lining up while Simon is fighting hard with the connectors over here and the files.
Is it the correct one?
Right. Nicolo.
All right. Okay, let me start the timer to be on time. Okay, thank you for having me. I'm going to talk about joint work with Rishan Liu at Stanford and Lester Mackey at MSR on model compression using generative adversarial networks. So Rishan did all of this work. Unfortunately, she couldn't be here, so I'm standing in for her. So why do people want to compress models? Usually when you deploy models in production or on memory or CPU constrained devices, you're limited in the complexity of the model that you can ship. And you usually suffer inaccuracy or performance as a result. Because of that, there's been a lot of research that is all mentioned. Wow, this is really fancy. That is all mentioned here in this reference list that allows you to basically take a teacher, and which is the complex model, and shift the inductive bias onto a student that is much cheaper to evaluate, but kind of preserves most of the accuracy of the teacher. Of course, you can do it. You need some data to do this induction task, and you can use training data. You can use unlabeled data that you have set aside before, or you can just augment the training data. We show that if you use training data, that doesn't lead to great results, and we show that augmentations are complementary to our method. But of course, the gold standard is still to use side data that is unlabeled. So how does compression work? You basically have I'm going to use the unfancy thing. You have some training data, you use it to train a teacher. Let's say that you have a source of unlabeled data on the side. You can show the unlabeled data to the teacher generates prediction, and you pass the unlabeled data and the predictions of the teacher to a student. The student minimizes an L2 loss, for instance, between the logits of the teacher and its own logits. Of course, and that's the point of our poster, when you having unlabeled data is kind of like a rare case. And so what you can do is you can approximate the data distribution, the training data distribution with a GAN, and then draw samples from it. And that allows you to interpolate between training samples that you've observed. And we show that this works very well in practice. And just as, just to give you an impression of the results, we can compress 300 trees in a random forest down to 1 tree. And we show that in general, augmenting the original training data with data sample from the GAN always performs better than just using the training data. And across a bunch of different tabular data sets, we show that at a loss of between 0.2 and 1.7% in accuracy, you can compress models down to a size that results in an increase in throughput from 35-fold to 375-fold. And this also works for, as you would imagine, for convolutional neural networks on Cepher 10. You can compress pretty expensive models down to much cheaper models with a relatively small decrease in accuracy. But maybe what's more interesting for this crowd and is also the kind of like was mentioned in the talk before, you can actually use these notions from compressions to score the quality of generative adversarial networks. So for instance, let's say that in these experiments, you have some real data, you have some GAN that was well trained, so fewer artifacts, the samples look pretty realistic as much as they can given their small size. And then you have a GAN that is not well trained, that has a lot of artifacts and not very high quality. You see that actually, as it was shown in the previous talk in other circumstances, the inception score doesn't really capture the image quality, or the quality of the samples rather. We devised, during the development of this paper, we devised a compression score, which is essentially the ratio between the accuracy of the student trained on GAN data versus the accuracy of the student trained on the real data. And we show that this actually captures the quality of the GAN much better. And as you would expect, it scores the inferior GAN worse than the well-trained GAN, which doesn't happen for the popular inception score. So if you're interested in learning more, the poster is on the floor in the corner. I'm going to put it up again. There is a paper that we just came online on arXiv today if you want more details.
Thank you. We have time for one quick question. Okay. Oh, there's a question.
If I just give a blank image, what would be my compression score?
To sample or to train the?
No, I mean, so you're mentioning some score with respect to.
Well, a blank image, I have no idea. I don't think it would be very good because it would be outside. So if the GAN generated a blank image?
No, I'm just giving you a blank image. What would be my compression score?
Depends if it's part of the, it depends where, if it's part of the original data distribution. If you generate a you try to approximate a data distribution that contains blank images, it would be good.
Okay, thank you.
All right, let's thank the speaker. All right. For our next spotlight is Chidubem. Okay, I hope I got it right. Thank you.
Hi. In this work, we present an adversarial labeling game for learning from weak supervision. Now, what is weak supervision? Weak supervision trains model with unlabeled data and noisy indicators of the target distribution. Now, if you've worked with weak supervision before, you know that one of the challenges when learning from weak supervision is there may be bias in the error made by the weak supervision signal. So if you train with multiple weak supervision signals that make dependent error, this bias will be propagated into the model. So to tackle this problem, we propose a two-player zero-sum game. The game is between an adversary that chooses labels for the training data and a model that tries to minimize the error made by the adversary. So the intuition behind this objective function is we want to train a model to perform well under the worst possible condition, and the condition being considered are the possible labeling of the training data. So, so you can see in the equation, the adversary maximizes, how do I go back? Okay. The adversary tries to maximize the error rate of our objective, and the model minimizes these error rates. Now, to efficiently optimize our proposed method, we use primal dual updates for an augmented Lagrangian approach. Now, the benefit of using this is instead of trying to solve the inner maximization at every iteration, which is really expensive, this way we can take gradient steps for each of the variables that we care about, and at every iteration we partially solve the optimization. So okay. So the Y is the adversarial label, the Q's are the weak supervision, and the B is the bound of the estimated error for the weak supervision. And here we update our model. We update theta via gradient descent. Then we do a gradient accent step to update Y, which is the adversarial label. Then we also update the KKT multiplier for the augmented Lagrangian. Now, when we tested our method on different data sets, we found out that we performed well, we performed really well, and we beat the baselines that we compared to for most of the data set that we test on. An example, we'll be focusing on fashion MNIST, which is an image classification data set. We train with weak signals that are marginally better than random, but our method is able to train a model to get up to 92% accuracy. Now, this other experiment is an experiment whereby we train a model with a good performing weak signal and multiple copies of a bad performing weak signal. Now, what we find is that while the baseline methods are confused by the redundancy, the repeated bad weak signals, our model, which is here is called our adversarial label learning, it's able to maintain its accuracy. The redundant weak signal doesn't give it extra information, so it's not confused by the errors in this weak supervision. So the accuracy maintains and doesn't degrade with multiple copies of the weak supervision, of the bad performing weak supervision. So what's the takeaway point here? So we've presented a novel method for learning from weak supervision, and the name of this method is called adversarial label learning, and we present it as a game between an adversary and a model. Now, we've shown that our method is robust against weak supervision signals that make dependent error, and our optimization approach allows for inexpensive updates to all the variables under consideration. Now, if you want to learn more about this, we have a poster up there, and also we have a full paper accepted on this at AAA 2019. So I'll be here to talk more about it if anyone wants to know more. Thank you.
Thank you. Any questions for our speaker? All right, let's thank the speaker one more time. All right, so for the next spotlight, we have João.
Good afternoon. I'll present our work in which we explore the multiple discriminator setting for GANs, multiple objective optimization. GAN training is sometimes too easy for discriminator. It's too easy for it to tell apart real and fake samples. Recent literature introduced the multiple discriminator setting, trying to overcome this issue. So what we do is to define the generator training in this setting as a multi-object optimization problem. This is the setting that we build upon. It was introduced by Nishabur and his collaborators in 2017. And what they do is they have one generator and a set of discriminators, and each discriminator sees a randomly projected lower dimensional version of the inputs. And what they claim is that discriminating real and fake samples in this space is harder, and this kind of regularizes the discriminators. And they also prove that the more random projections you are able to approximate, the closer you are in the original space as well. So what they do is pretty much trading a hard problem for a set of easier subproblems. So what we want to do is to minimize a set of non-negative costs. And the first thing we tried was the multiple gradient descent algorithm, in which like we have a set of gradients from each cost, and we get the minimal norm element within the convex hull defined by those gradients, and we do a lambda step on this direction, on the negative direction. And it's proved that when the costs are convex, this is a common descent direction for all of the costs simultaneously. The thing is, finding the minimum norm direction in this convex hull is too expensive if you have a big model. So we tried other alternatives as well, and we did an empirical comparison of different strategies for doing that. So this is another alternative that we tried, the hypervolume maximization. So in this figure, there's an illustration of the case in which you have just two discriminators. So we define a shared upper bound on all the losses, that eta, that we call Nadi point. And we want to maximize the highlighted region. And if we do that, we are simultaneously minimizing all the losses. So we define the loss as the negative log hypervolume. And when we get the gradient of this loss with respect to the parameters of the generator, what we see is that we end up getting a weighted sum of the gradients. And the discriminators against which I perform worse have a bigger weight. So, and we can control this effect by controlling the magnitude of this guy here. So what we do is we try many different schedules, and we find this one to perform well empirically. And we keep decreasing eta so that we keep this effect relevant throughout training. So those are some results that we got for Eminis. What you can see is that here the red line is a random generator, the blue line is real data, and we have the four methods. So getting simply the average of the gradients, getting the GMA approach, which is weighting them by a soft maximum losses, hypervolume maximization, multiple gradient descent. What you can see is that MGD performs the best, but it takes a long time to converge. So what we argue is that in this trade-off on the right, in which you have the best FID achieved and the time to achieve it, hypervolume maximization has the best compromise. So MGD is better, but takes a while to converge. This is another result that's interesting. What we study here, the diversity of the generator in this technique setting, in which we know the number of modes that we have. And what we show is that by simply increasing the number of discriminators that we train against, we can go from a very low coverage to state-of-the-art comparable numbers. So just to summarize the presentation, we find the multiple discriminator gun setting with multiple discriminator training. We show it's a practical approach to trade the extra cost into high quality samples. And we also show that it yields high diversity and sample quality, and it makes it easier to find a working set of high parameters. We have more results in our poster right over there, so come and talk to us.
Thank you. Any questions from the audience for our speaker? I have a quick question. It seems like you introduced a new hyperparameter here, right?
Yep.
And this hypervolume maximization scheme, and it's either what's the new hyperparameter here?
It's eta, the nadir point. Yeah.
Right. So how much effort goes into tuning this hyperparameter? And is the same hyperparameter used in all experiments?
No, it actually makes a difference we have to tune it. It makes a difference in the scores, but we have a result that's not in presentation, but it's in the poster, in which we show that when you have the more discriminators you have, the more robust to this hyperparameter the results get. So it is important, you have to tune it. It's an extra effort that our algorithm introduce, but if you can afford more discriminators, this effect goes away. So.
All right, any more questions? Thank you. Okay, so our next spotlight is Mandikal?
No, I'm Steffen.
Stefan, I'm sorry. We have Stefan for our next spotlight.
Hi, yes, exactly. So, hi, I'm here today presenting joint work with Vikram Mandikal on our instance segmentation framework, where we have introduced a conditional GAN to improve the segmentation. So instance segmentation arises naturally in many domains, and this is one of my favorite. So on the left-hand side, you can see a tissue, fruit fly in brain tissue, and what you want to do is, so you want to find the individual neurons here. So this is the segmentation problem, and you can solve this by first predicting probability or affinity maps that basically indicate whether two pixels are in the same cluster or not. And then you apply a clustering algorithm, such as the mutex watershed that we've seen in the title. In this short talk, I'll only focus on the first arrow. So how do we predict good affinities? And in this work particular, we have looked into natural images. So this is an example image of the BSD 500 segmentation database. So why should we care about GANs? So how can we improve the segmentation? Well, in this toy example, you can see two images where I've artificially introduced a hole and a shift, and shifted the affinities. And you can see that the pixel-wise loss is much more sensitive to a shift in the affinities than the small introduced holes. Whereas, and this slight spoiler, whereas the discriminator that we train in our framework is much more susceptible to the holes. All right, how does that work? Well, in the classical setup, you would just have a generator network conditioned on the input image X, and we output some probabilities. So you can see in this image they are very imperfect, and what we would like them to look like is affinities generated from closed contour label images, right? And so you can see this is a perfect setup for a conditional GAN. So here now I've introduced the discriminator here that gets input images X and the matching contours, or pairs of input images and generated contours. We can see that this improves our segmentation performance, but unfortunately it also has a very unstable training process. So in the second step, we introduced an auxiliary task. And our intuition was that the first task of predicting the affinities, which are very non-smooth, is a very hard target for the generator. So what we did is we gave a second generator a smooth target, which is the distance transform. Starting from the affinities, you can basically measure the distance towards a boundary, and you can give this as a target. So now we have two conditional GANs, and where the two generators importantly share most of their parameters. So this is a classical multitask approach, and we can really see that in our experiments that this combination improves the segmentation score drastically. So this is an example image without the GAN, with GAN, and with GAN and auxiliary loss, where you can really see that it learned to close the contour lines. This is a second example. So the final question that we had was really, is this auxiliary task the reason for the performance improvement, or is it the GANs that we've introduced, right? And for this reason, we done an evaluation study where we have tried all of the combinations of GANs, not GANs, and auxiliary losses. And we really find that introducing the GANs in this framework gives us a significant improvement. Finally, since we have the GAN discriminator, we can actually train on previously unlabeled data, such as like we've seen in the talks before, and this also additionally gives us a slight improvement. All right, with this, thank you very much, and if you have any questions, please come to my poster.
Thank you. Thank you. So any questions before the posters? Right. Oh, that's my bad. Okay. So let's thank the speaker again.
Thanks.
And we're setting up for our panel, and before we have our final poster session for the day. So we have a half-hour panel discussion with some of our speakers. So we are going to quickly take a couple minutes to set up.